Okay, for reasons of time, I will not expound on what an honor it is to be here and etc., etc. So I'm going to say a little bit about Harvey's work on interpretations and especially his early work. So, yeah, I had to pick the photo of the internet because I didn't have real photos of Harvey. So this is the man himself. And this is the book. So I think it was very fortunate that this book came out, and so it was. It contained a number of perfect expositions of Harvey's work, but especially for me, Craig Smorinsky's treatment of non-standard models and related developments was extremely useful. So, and I think we should be very grateful because already officially Craig's paper was about non-standard models, but it was full of other goodies, right? There was something about Friedman flag, there was things about Friedman on interpretations, etc. But and not just expositions, but all kinds of very nice philosophical remarks about the project, etc. So here, thanks to Dirk and Doki van Dalen, I have a photo of Craig. So this is. And probably this is about the age that he wrote this, right? So that's. Sorry?
A few years old.
A few years older. Okay.
No, this is photographed a few years.
Yeah, it's a few years, definitely. But it was taken around the time that he wrote the paper that we're discussing. Okay, so to introduce the stuff, I want to say a little bit about what interpretability is. So. What is interpretability? Well, a theory U is interpretable in a theory V if you have a translation of the one in the other, right? So you have a translation tau such that every theorem A of the given theory U is such that the interpreting theory proves its translation. And go, okay, so then what is a translation? And I think the real idea is simply that the translation commute with the logical connectives. Only if you think about what that means, you get more and more complicated variations, and so that's part of the problem. But for our purposes, let's just keep it at that and just add that we do that plus domain relativization, right? So the quantifiers are not just translated as themselves, but we simply have a stipulated domain, and we relativize the quantifier to the domain, right? So that's the main point. And so all the other refinements we blissfully ignore. So there are really two ways of thinking about interpretability, as a notion that fits into some category, or it as something like a generalization of provability. And so here we think of it as a generalization of provability, and so this sign is supposed to be suggestive of that way of looking at things. So I read this, V interprets U, or U is interpretable in V, etc. Okay, so interpretability has all kinds of uses, right? So, for example, explication of the identity of it, or the individuation of a theory independent of the signature, blah, blah, blah. So there's lots of ideas. But in our context, we're really mostly interested in measuring the strengths of theories. And so interpretability is an extremely good measure for doing that. And, for example, it's much better than the very popular notion of conservativity. So in reverse mathematics, very often people use conservativity, and I have had strange discussions with distinguished people like Yannis Moshevakis, so about GB, right? So GB is, according to received wisdom, precisely as strong as ZF, but actually it's one Gödel up. So GB proves the consistency of ZF, but of course not in the ZF language, but in another choice of the language. And so, so it is better. So another maybe notion to compare theories is relative consistency, and so in a moment I will tell you how bad relative consistency is and how good interpretability is. And so measuring strengths, of course, so Sam just talked about that. It has its natural home in things like reverse mathematics. So the common examples, ZF and PA and a suitable theory of syntaxes, or syntax. Robinson's arithmetic, Q interprets a fairly decent arithmetical theory, I delta 0 plus omega 1, in which we can do syntax, etc., etc. And so this is really Nelson's program, right, to do the bootstrap, to build that interpretation. And, of course, some results from the past, namely plane geometry in the Euclidean style gives you plane geometry in the hyperbolic style. Okay, so we need to get off the ground for the story. I need a second notion, and that's sequentiality. So, so logicians and mathematicians always talk about series that have good properties of coding, but it's little known that there's a really very stable and good explication of what that is, right? And that stable notion is sequentiality. So if a series is sequential, then if and only if it supports a good theory of coding, and that's in fact a good theory of sequences, and the sequences are supposed to work for all the objects of the series. So not just some selection of the objects, but all of them should be orderable in sequences. Finite sequences, yes. Okay, so now the notion of sequence, so in some of my papers there are definitions, and it's 20 because you need numbers to do the projections, so you have 20 axioms to really explicate what the good theory of sequences is. But fortunately there's an extremely simple definition, and so that uses adjunctive set theory. And so a series is sequential if and only if you can define a predicate posing as the elementhood predicate, such that for that predicate our theory can verify adjunctive set theory, and that tells us there is an empty set, and whenever you have a set and an element, you can adjoin that element to it, right? It's simply X union singleton Y, right? Only we don't have extensionality, so there can be thousands or even infinity of empty sets, and there can be an infinity of adjunctions. And in fact, the idea of having extensionality is a very bad one because it's a complicated property to get, and you never need it for the coding. So, someone has a
define a predicate epsilon without parameters, with parameters.
Yeah. Okay. So there are all these detailed width parameters, and you could also make it multidimensional, etc. But let's not worry about. But indeed, there are some technical details here. Okay, and using a substantial bootstrap that is due to various people like Nelson and Putlak, you really can show that you can have everything you want as soon as you have these two simple axioms. And of course, all the theories that are not in the tame world, so the theories that I think most of the people here study, are sequential, right? So PA minus, the theory of discretely ordered commutative semi-rings with a least element. Q is not, so that's also interesting. But PA minus, very close to Q is. I delta 0 plus omega 1, so Harvey's favorite theory that he calls EFA, so elementary arithmetic, so I delta 0 plus the totality of exponentiation, PRA, I sigma 1, piano arithmetic, AC 0, ZF, Gödel-Bernays set theory, etc. Right? All these things are sequential.
A typical theory that's not sequential would be these so-called tame theories.
Yeah, so everything in the tame world is definitely not sequential. Of course, typically sequential theory are essentially undecidable. So as soon as you're looking at something decidable, it's clear that it's not going to be sequential. Now, it turns out that if we zoom in on the finitely axiomatized sequential series, these have all kinds of amazing properties, and two of these amazing properties were discovered by Harvey. So one of them is the Friedman characterization of interpretability, but before, to warm you up, let's very briefly look at relative consistency. So relative consistency, you would think that simply when the consistency of V implies the consistency of U, but since we have classical logic, it doesn't mean very much, because you have classically this implication is true even, well, whenever V is inconsistent or U is consistent, right? So to make it a meaningful notion, we need some base theory, and we simply demand that it's provable in over the base theory, right? So, for example, Pfefferman discusses this notion, but it's a very bad notion. So one thing is, of course, in general, it is not the same thing for whatever base theory we take. It's not going to be the same thing as relative interpretability, because this thing is, of course, complete sigma 0, 1, where Shavrikov showed that interpretability in general can get as complicated as complete sigma 0, 3. But so the real reason that relative consistency is so bad, that is very strongly dependent on the chosen axiomatization. So in the terms of the art, it is an intentional notion. And so specifically, for example, you can find, so given whatever base theory you take, but let's fix EFA or EA as the base theory, you can always find an axiomatization of PA for which PA is stronger than ZF, so strictly stronger if you wish. And then you could say, well, this is sick, right? So this is a completely artificial thing, but no criterion that you can give, no technical criterion is going to fix it, because the most natural way of axiomatizing a theory is an axiom scheme, right? But we cannot even prove that there's an axiom scheme that has that has this property. So yeah, there's simply no way to get it right, at least if you want to eliminate simply recognizability by a professional mathematician, whether something is okay or not, right? Then it's, of course, still. Okay, so the interesting thing is that in one case, that's Harvey's discovery, in one case, interpretability and relative consistency coincide, but it's a very special case. So the series should be both finitely axiomatized and sequential, so it should have good coding. And so what we then have is that A interprets B if and only if elementary arithmetic proves the restricted consistency of A, the restricted consistency of B from the restricted consistency of A. And so restricted consistencies here means that we restrict the allowable formulas in the proofs to have a prescribed complexity, right? And so my favorite measure of complexity is depth of quantifier alternations. So rho A is the complexity of A, so we simply only allow formulas of lesser or equal complexity of A here, etc. So I'm always a little bit uncertain whether we shouldn't add here some constants, 100, 100, or because of some technical detail that we have to count some brackets or whatever, right? But I think this works. But if you're uncertain, let's add 10,000 to the row of A to get it right. So that's restricted or bounded consistency. But if you're uncomfortable with that, so everything that the proof series knows and loves also works. So you could also substitute cut-free, tableau, or Herbrand consistency for bounded consistency, because all these things are multi-exponentially related, and hence they're equivalent over EA, right? It's only a multi-exponential and not a super-exponential transformation. So if you're nice for this Friedman characterization, you can see that it also can be given a different, very attractive form. And namely, look at the map, the map that maps A to EA plus the restricted, I have here still the modal notation. So this should have been con con rho A. So we map A to EA plus this consistency statement. And that turns out to be an effective isomorphism between the degrees of interpretability of the finitely axiomatized sequential series and the pi1 extensions, by single sentences to be sure, of EA. And so these ordered by derivability. So you get here a reduction between interpretability, which is in some sense a more complicated notion, prima facie, and derivability. And so this alternative form of the Friedman theorem is extremely useful because some very clever people have done a lot of work, so and specifically Shavrikov and Lindström worked on these, the pi1 extensions of series, and fortunately they go precisely down to EA, so not below, that's a different world. But so all their work works for EA, and so we can simply transfer everything they did to this degree structure. And for example, I just took one example, the first order series of the sequential degrees of finitely axiomatized series is not arithmetical, right? And so that's due to Shavrikov. But there are many other results. Okay, so how much time?
Another 10 before, or it's 10 minutes.
Okay, so now, of course, things like the Friedman characterization can be lifted to the infinite case. And so we have the so-called Mo functor. So if you have a series Mo, we can map it to an appropriate weak series plus all the restricted consistency statements for that weak series. And so if our theory V is sequential, so then we can have a similar characterization as the Friedman characterization that tells us that V locally interprets U if and only if the Mo of V implies the Mo of U, where local interpretation means that V interprets every finite subseries of U, right? So there's a whole number of variations of the Friedman results in its direct Umfeld. Okay, but let's quickly move on because I want to show you a second theorem which I tend to think is a deeper insight. Is namely Friedman on phaseful interpretability. So the definition of phaseful interpretability is the same as interpretability, only we have here an if and only if, right? So U proves A if and only if V proves its translation. So that's the difference. And so it's phaseful. And phaseful interpretability is slightly better than interpretability for preserving certain properties. For example, if the interpreting theory is decidable, then so will be the interpreted theory, at least if the interpretation is phaseful, right? Otherwise, no way. And so that this notion of phaseful interpretability is, I think, in some sense, is a good notion. And so Harvey proved that if A is consistent, so I'm always forgetting the consistent, so I'm happy I have it here, finitely axiomatized and sequential, then every interpretation of a series U in A can be improved to be a phaseful interpretation. So that's the basic idea. So the Friedman result was published by Craig in 85 and presumably obtained between 75 and 80. But completely independently, at least, Jan Krajicek rediscovered maybe not the precise theorem, but one that is very close to it in the notes of proof of falsehood in 87. So that's quite related. And so this has some consequences. So in some sense, one consequence of the theorem is that whenever you cannot make the series, the finitely axiomatized series, in a serious way sigma unsound. Of course, you can add, given such a series, you can add, for example, its own inconsistency, but then you can go to a definable cut of its numbers, and there the inconsistency will disappear. So there's no way that you can preserve the inconsistency. And so, for example, if you take I sigma 1 plus incon I sigma 1, you can always beat the inconsistency. You can so definable cuts are in some sense notions of smallness. You can say a number is small if it's in this cut, and for the small, you can choose the cut such that the inconsistency is not in it. Okay, and so you can improve this kind of insight a little bit. So suppose that A is a consistent, finitely axiomatized extension of some weak arithmetical theory. Then you can find a definable cut and a model M, such in that model all witnesses of the false sigma 1 sentences are above this cut, right? So you can always, so in this model you can even defeat all wrong lying witnesses of the sigma 1 sentences, right? You can beat them all. Okay, for applications, the Friedman theorem is not the most, in that form it's not very directly useful, but you can strengthen it a little bit, and then you can use it for lots of things. So because the strange thing is that the property that Harvey discovered is preserved under mutual interpretability, and so properties are almost never preserved under mutual interpretability. But if we at least when we start with a consistent, finitely axiomatized and sequential theory, and if something is mutually interpretable with it, then it again has this property. And in fact, in the train coming from Rotterdam to Antwerp, I realized that probably something even stronger should be the case, but I haven't written it down, so I cannot tell it here, and also I have no time for it. So Friedman's result has some nice uses. So for one thing, of course, a lot of well-known theorems follows immediately from it, right? So the non-finite axiomatizability of PA, the Real-Nardevsky's theorem, immediately follows. Why? Well, suppose PA were finitely axiomatizable, so then PA plus incon PA is also finitely axiomatizable, but incon PA, because all definable cuts of PA are the trivial one, and so you would have incon PA on all cuts, and that would contradict Harvey's result. And similarly, of course, for in fact arbitrary sequential series with full induction. So that's so Ali tells me that's Montague's result, so I hope that's the correct assignment. It's also a very rich source of counterexamples. So, for example, there's this notion of the logic of a theory, so all the schemes of a theory, and almost in all cases, the logic of a theory is just predicate logic, right? If we fix a signature, look at the logic of some theory you know and love, you always get predicate logic. But in fact, we can find arithmetical theories, for example, an extension of I sigma 1, such that the predicate logic of it is complete pi 0, 2. So the last thing I have still, I'm looking at the chair, so I'm not going to do the proof then, but just describe it. So if you look at model theory book, it's interesting so that model theorists never look at interpretations in a syntactical way. They simply say, well, every model of one theory has an internal model of the other theory, right? That's the model theorist notion. And in fact, God is with us because in all cases I know this is really equivalent to interpretability. And in fact, it's an exercise in the fat Hodges that tells us that as long as our theories are finitely axiomatized, in fact, it's a theorem that model interpretability and interpretability will coincide. But in fact, it doesn't coincide in general. But so I don't have any elementary example of it. I'm sure that if you sit down for 3 days or well, maybe 1 day and work hard, you can find an elementary example. But given Harvey's theorem, there's a deluxe example. So what you simply do is you take, let's say, I sigma 1 or any other finitely axiomatized sequential theory and simply add all the inconsistency statements on all the definable cuts or on all the definitions of arithmetic. So by, well, in fact, the strengthening of the Friedman result I showed you, it immediately follows that this theory is not interpretable in U, but it is model interpretable. So look at any model of I sigma 1. So that will either contain all the inconsistencies or not, right? If it contains all the inconsistencies, we're immediately done. But if not, so there is some consistency statement somewhere. But then you apply the second incompleteness theorem that tells us that if I sigma 1 is consistent, then this theory is also consistent. And then you do the Henkin construction to construct an internal model of that theory U, and so then you have the Henkin interpretation of U. So in all cases you have it. And if you look at the proof, you see what is going on here, right? We can almost specify this interpretation, but we need an infinite disjunction, and this infinite disjunction is not present in the first order language, and so we cannot do it. But somehow in the model interpretability case, you can simulate the effect of the infinite disjunctions. Okay, is this the last thing? Yeah, so that was it, and thank you.
Thank you very much. We usually take 30 minutes, but I suggest that we continue with the next speaker, unless we have some time for break at the end.
Okay, good.